In the previous video we proved that P implies Q. If P is true, Q is true. Now in this video we prove that Q implies P. If Q is true, then P is also true. That will make P and Q equivalent statements. Okay. So what is Q here? There exists a onto function G from N to A. So we have to prove that there exists a one function from A to N. Okay. So let's try to do that. So what is now given for us is there exists a G from where to where? From N to A. From N to A. Set of all natural numbers. Set of all natural numbers to the set A, given set A, G is onto. G is onto. There exists a onto function or surjective function. Now to prove what? To prove that there exists one function f from A to N. Okay. So how to prove this? Let's go one step. So we have to construct this f using the given G. That's how the proof that's how the proof goes. So we have to construct a f which is 1 using the information that there exists a G which is onto. Okay. So take this G and define f in this format. So for A belongs to A, define f of A as G inverse of A. So G inverse of A will have may have multiple elements in N. So you take the minimum of that. And minimum exists because G inverse of A is a subset of N, is subset of set of natural numbers. So every subset of set of natural numbers has a minimum. So define f of A as that minimum value. So pre-image of A, you take every small a belongs to capital A, you take its pre-image. And in the pre-image set, you choose the minimum one. Now this value f, or this way if you define f, this will be a 1 function. So let's prove that. Okay. Let's try to prove that. So we prove in this format. So what do we prove is that if you take two different elements, so if you take A1 and A2 both in A with A1 not equal to A2. Suppose A1 and A2 are not equal and both are in A. The images of this also should not be equal. Then the function is 1. The images of A1 and A2, if they are not equal, then function is 1. Let's see. Now we prove that f of A1 and f of A2 are not equal. So how to prove that is, what is f of A1? F of A1 is minimum of G inverse of A1. You see this set, and you also see this value, minimum of G inverse of A2. You consider these two. These two are two numbers. Okay. Now G inverse of A1 and A2 or G inverse of A1 set and G inverse of A2 set is non-empty. That's why this minimum is defined actually. Here we use the minimum because G is given as a onto function. So G inverse of A exists. It is not an empty set. And it exists, therefore f of A is well defined. F of A is well defined. So f of A is a function now, clearly. Okay. Now if A1 and A2 are not equal, then always its inverse images are also not equal. That is because G is a function. If you take two different elements in the codomain, you take the inverse images of those sets, inverse image of those two elements. They will be completely disjoint. Otherwise, it is not even a function. So therefore, these sets G inverse of A1 and G inverse of A2, these sets are disjoint. Therefore, their minimum also will not be equal. Okay. So therefore, these two sets. Okay. I'll just without the minimum. Suppose say without the minimum, these two sets are disjoint sets. Okay. Are disjoint sets. Are disjoint sets. Thus, their minimums are also not equal. Okay. Thus, what happens? Their minimums, minimum of G inverse of A1, a bit not clear here. G inverse of A1 is not equal to minimum of G inverse of A2. These two are not equal. But what is minimum of G inverse of A1 is f of A1, which is not equal to f of A2. Okay. Thus, what we have is that if you take two distinct elements in A, their images under F is also distinct. Thus, proving F a 1-1 function. So, what we proved, we assume that G is onto. There exists a G which is from N to A is onto. And we proved that there exists a function F which is 1-1. In the previous video, we proved that if there exists a function F from A to N which is 1-1, we proved that there exists a G from N to A which is onto. So in this way, these two statements P and Q are equivalent. Okay. So now if you want to prove a set A is countable, you can either prove that there exists N to A onto function, or you can prove that from A to N there is a 1-1 function. So in any ways you can prove that, okay, which will make the set A countably infinite set. Okay. Thus, or actually may not be countably infinite. It's a countable set. It's a countable set. I'm sorry about that. A countable set. Thank you.